Hello everybody, welcome, and thank you so much for joining us. In the audience today, we have representatives from across the quantum ecosystem, including industry and academics from around the world. My name is Gillespie. I am the VP of Applied Research at Riverlane. My role at the company is to oversee the full research portfolio and set the strategic direction for advancing fault-tolerant quantum computing. This enables us to develop the many wonderful results that ultimately define the specs for the products that we want to build. Last month, we announced our QEC technology roadmap to utility-scale quantum computing. Today's webinar is a chance to dive a bit deeper into our approach and give you the opportunity to ask questions to myself and later to our brilliant panelists. A quick reminder of today's agenda. Following the roadmap presentation and a short Q&A session, I'll be introducing our panel, which brings in world experts from across the ecosystem. The panel session will be split into two conversations, first focusing on the existing challenges and key milestones towards utility-scale quantum computing. Following that, part two of the panel will discuss themes around the role of HPC and AI in quantum, as well as the tools we should develop and ways we should collaborate to continue to accelerate progress. Before we close, there will be time for questions to any of our panelists. You can start submitting your questions now. Head to pigeonhole.at or scan the QR code on the screen now. Type in QEC Roadmap 26 to access this event and add in your questions. Okay, let's get started. Our mission is to master quantum error correction and unlock a new age of human progress. Our roadmap is the mechanism by which we achieve our mission. We believe our approach will accelerate the industry by years, and I'll explain why in this presentation. This is Riverlane's QEC technology roadmap, and I want to walk you through it because I think it tells a genuinely exciting story. The structure has two axes, time running left to right, from 2025 out to 2033 and beyond, and two product lines running top to bottom. DeltaKit, our software environment for QEC, and our real-time QEC system DeltaFlow, which is the hardware-integrated QEC engine. Everything here is built around a single goal, making quantum computers useful sooner. That's the problem Riverlane exists to solve. We're not pointing at a distant horizon. We have a concrete stage plan to get there, and we're already well into executing it. The roadmap is divided into eras, each with a headline milestone. The first, 2025, was the first full quantum error correction system. We delivered on that milestone, and DeltaFlow 2 is now operating in several national labs and hardware companies all around the world. We're now in 2026, moving into the era of fault-tolerant quantum computers. From 2028 onwards, fault-tolerant circuits, first algorithms, and ultimately utility-scale quantum computing. Each era builds on the last, and the foundations of the first are now firmly in place. Before we dive in, I want to define one metric that runs through everything you're about to see. That metric is the QOP, the reliable quantum operation. And by reliable, I mean error corrected. Think of a QOP like a clock cycle in a classical processor, the fundamental unit of useful computational work. More QOPs per second means a more powerful machine. But the cost of a QOP isn't the same for every quantum technology. It depends on the underlying architecture. For systems based on topological codes and lattice or generalized lattice surgery, a single QOP corresponds to roughly d rounds of QEC cycles on a logical qubit, where d is the code distance. For architectures using transversal logic, it can be as short as a single QEC cycle, a potential speed advantage there. And some systems may combine both, transversal gates where they can and lattice surgery where they must. So the QOP is a nuanced metric, but that's precisely why we find it useful. It forces an honest comparison across different hardware platforms and architectures. When you see the QOP numbers on the roadmap, you're seeing our best assessment of real computational power. The real-time QEC system is the heart of what makes everything possible. The physical qubits of a quantum computer are noisy, fragile things, prone to errors. The only way to run a useful quantum computation is to detect and process those errors faster than they accumulate in real time while the computation is running. That's what DeltaFlow does. Our current product has been built and optimized for solid-state qubit systems, where QEC cycle times are very fast, on the order of microseconds. That speed puts enormous demands on the decoder, and we spent years engineering a system that can keep up. But the quantum hardware landscape is broader. For example, AMO systems operate with slower QEC cycles, and their architectures change the decoding challenge in interesting ways. We've been developing novel techniques specifically for these architectures, and that work is very much part of our roadmap. So on the roadmap, you'll see both a product track and an innovation track running in parallel. That's deliberate. It's how we ensure that as the hardware landscape evolves, our QEC solutions evolve with it. Alongside the real-time decoding engine, we have DeltaKit, our software environment for quantum error correction. Think of DeltaKit as the interface layer between the algorithm and the error correction machinery. It lets researchers and hardware partners work at the level of logical operations without needing to understand everything that's happening at the physical gate level underneath. It also enables researchers to explore and validate a variety of QEC approaches. The critical thing about DeltaKit, though, is that it's not just a research tool. It's the foundation for everything that follows, the software stack that scales with the hardware as we move through the roadmap. Let's look at what we delivered in 2025. The milestone was quantum memory, the ability to maintain a long-lived logical qubit. This is one of the foundational steps in quantum error correction. It sounds simple, but it has taken the field years to achieve reliably. On the DeltaKit side, the key achievement here was reconfigurability. Rather than building a one-trick system, we used DeltaKit to program the hardware to handle a whole variety of quantum memory experiments. One piece of hardware, multiple experimental configurations, all managed through software. That's the power of having a proper software layer sitting between the algorithm and the machine. What I'm proud of is that this wasn't lab science. This is software and hardware that ships, that partners ran, that produce results you can benchmark and publish. We built the foundations correctly, and that's what gives me confidence in everything that follows. Now, in 2026, things are getting really interesting. The headline milestone for this year is quantum gates. Specifically, we're progressing to the first types of genuine quantum computation, Clifford logic. This is a significant step. Moving from quantum memory to quantum gates means we're no longer just preserving information. We're starting to compute with it. And again, DeltaKit is what makes this programmable. Just as we used it in DeltaFlow 2 to run a variety of memory experiments, we're now using it to program the hardware for different computational experiments. The software layer is what gives us that flexibility, and it's what will allow our partners to do the same. At the same time, we're making the decoder at the heart of the system more accurate. That matters because decoder accuracy directly translates into QOPs. The more reliably you can correct errors, the more QOPs your system can produce. This is where the engineering work on the real-time QEC system really starts to pay off. Looking further out to 2028 to 2032 is the era where quantum computing takes its next major leap. The first milestone of this era is non-Clifford logic, the defining capability of DeltaFlow 4, the first QEC stack that meaningfully delivers these operations. If Clifford logic is the first chapter of quantum computation, Non-Clifford gates are what open up the full story, and where real-time QEC is fundamental. These operations are necessary for algorithms that will outperform classical computers on problems that matter. Delta-Flow 4 will apply to small-scale systems, but that's how every important capability in this field has started. Then, as we move into the megaquop era, we scale. The systems that demonstrated non-Clifford operations at small scale become the foundation for much larger, more powerful machines. And critically, this is also where our real-time QEC products begin supporting multiple leading qubit modalities. We're committed to making fault-tolerant error correction work across the hardware landscape, however that support is ultimately packaged. And beyond this, we reach the teraquop era, fault-tolerant quantum computing at utility scale, delivering computational power that surpasses classical computing across multiple domains. That's the destination this entire roadmap is building towards. And with the foundations we're laying now, it's a destination I believe we can firmly achieve. And so we come back to the full picture. This is a clear, staged engineering path from the foundations we laid in 2025 to fault-tolerant quantum computing at utility scale. Each era has a concrete milestone. Each product has a defined capability step. For those of you in the hardware community, quantum hardware community, our ambition is to support all leading qubit modalities. We're not betting on a single technology winning. We're building the error correction products and expertise to work across the landscape, and we want to work with you to make that happen. For those of you in academia, DeltaKit is the platform we want researchers using to explore, simulate, and benchmark QEC approaches. We want this to be community infrastructure. I'm incredibly proud of our team and what we've built, and I'm genuinely excited about what comes next. Cool. So that's the description of the roadmap. You've been hopefully submitting your questions online, so let's move to some of the questions from the audience. So if you give me a second, I'll just pull up this iPad and see how I do with technology. Okay. Just having a quick look. So I'll go for one that's got 3 votes. What are underappreciated aspects from a hardware maker perspective that pose a challenge to QEC that is not discussed as much today? Well, I definitely think some of the things I'm not sure that are underappreciated, but definitely certain some of the challenges are we're trying to get better rate codes, so QLDPC codes. And I think certainly some of the challenges there is how these QLDPC code needs long-range connectivity to be able to implement these higher rate codes. And certainly many of the challenges seem to be in various qubit types, how can you efficiently implement these long-range connectivities? Okay, so with superconducting qubits, that's a real challenge, right? Because it's a solid-state system and it's generally nearest neighbor connectivity. Now, along some of the hardware roadmaps, they're trying to generate these long-range connectivities. That seems challenging. In the AMO community, it seems like it's going to be much easier because they've got the reconfigurable arrays. That's certainly true in neutral atoms. But the interesting thing there is what is the impact on moving these qubits around, so the shuttling around of qubits, what's the impact there on the QEC cycle time, and what noise characteristics actually impact the QEC problems that the decoder needs to solve. So I think that's some really interesting problems there. So the next question from Anonymous is, do you have any opinions on which qubit modality might reach fault tolerant first? So at Riverlane, as I said in the presentation, we are open to working with all qubit modalities. And because of that, we do work with all leading qubit modalities. And because of that, we often get this question. We see lots of different qubit technologies, so we often get this question about which one will most likely reach fault tolerance first. My genuine answer here is it's too hard to say today. Each qubit modality has strengths and weaknesses, okay? And there's lots of challenging problems that everyone needs to overcome in order for their qubit type to be successful. And there is a world where we have a heterogeneous quantum computer where we're using different qubit modalities as well. So I'm going to give maybe an unsatisfactory answer, which is I don't know which one's going to be the first one, but I think there's really exciting and interesting problems that need to be solved across qubit modalities, and I'm really excited to see the progress there. Cool. Okay, we're going to now move on to the panel sessions. Let me first move on to the first panel. Let me quickly change slides. So introducing our first group of panelists, we have Tobias Thiele from Zurich Instruments. We have Frank Deppe from IQM. And we have Ben Yuen from Infleqtion. So please, can each of you give a brief introduction to yourselves and also your companies and what your companies are working on. Let's start with Tobias, please.
Yeah, hello everyone. I'm Tobias. I'm leading here the product management on the quantum computing side. So this also means that I strongly shaped the quantum strategy here. So we're at Zurich Instruments, we're a control electronics provider, really working here with on the control electronic side, but also going higher up in the stack and providing the software tools to this.
Cool. Thanks very much, Tobias. Let's move on to Frank.
Yeah, I'm Frank Deppe. I'm a principal quantum architect, sort of coordinating the big picture and the consistency of our tech roadmap at IQM. And the introduction of IQM is fortunately relatively simple. We are a company building quantum computers, so the hardware, and our modality, our preferred modality, which we are following, are the superconducting quantum bits.
Cool. Thanks very much, Frank. And Ben, let's get an intro from you, please.
Hi, thanks, Neil. I'm Ben Yuen. I'm the portfolio technical lead for quantum computing in Infleqtion. So I lead the UK quantum computing team here. Infleqtion actually covers more than quantum computing. We use atoms from quantum computing through to sensing. But we have a strong footprint here in the UK, an operational 100 qubit testbed here in the UK that my team has deployed and developed.
Cool. Thanks very much, Ben. So we've got some questions that we'll go through, and then reminder from everyone, we're going to, after the two panel sessions, we're going to relay questions from the audience back to both panels. Okay, so first of all, the first question, what are the main technical challenges you face as you scale your respective systems, specifically related to QEC and fault-tolerant quantum computing? Let's start with Tobias. What's your perspective on that question?
Yes, and thanks a lot. I think it's an actually interesting question. So for us as a control electronics provider, in the end, it's all about building the right architecture that is on the one hand simple, but also separates the areas of concern. So, and this means concretely for us, on the one hand, we have to really make sure that all the pulses come at the right time. This is not only a few pulses, but potentially millions of pulses on thousands of signal lines. And this is just something we cannot compromise, and we have to guarantee this. And this is something which now, with our latest architecture, can actually provide and guarantee by, for example, we have a built-in error detection. We have specific ASICs which sort of distribute a global clock, a global time across the different components in the system. And of course, also we have access to cutting-edge technology, also thanks to our mother company, Rohde & Schwarz, where we can actually then sort of synthesize these pulses that are needed to operate high-fidelity gates at scale. And then other concerns is rules how do we actually stabilize the quantum information, like do error correction in a quantum system? And here, let's be honest, no one really knows what the ruling architecture is going to be. So we have to really here supply the flexibility in the system. In the sense, not only just the tool set or each tool set, like different accelerators like GPUs, CPUs, FPGAs, but also the IP, like it's being provided here by Riverlane, which we provide in our collaborations. But also, of course, also have to understand how do you actually program this thing. So what is the right programming model that then allows the researchers to figure out how to actually decode down to this algorithmic error rates. And essentially, yeah, so if you're sort of comfortable on the technical challenges, but maybe also coming back to one of these underrated questions which was answered before, or which was asked before, is something which is often underestimated is actually then how do I make the system now work in a lab setting, or sort of really the lab integration from potentially software layers where you have automation workflows all the way to maintaining the systems continuously at the peak performance. This is actually a challenge which I think we will face going now further when we start to build these larger systems, and it's something where we have to really work together here in teams to pull off this challenge of stabilizing and mastering quantum error correction here.
Yeah, and so like as we said in our presentation, there's different error correction protocols for different qubit modalities. That certainly seems to be a thing that's going to happen. How much you talked about, like obviously synchronization of pulses. I mean, how much is this varying between, say, AMO qubits and superconducting type qubits, or like slow qubit types and fast qubit types, or is it just in some sense it's the same principle? You have to get everything highly synchronized. Maybe the speeds are slightly different.
Yes, exactly. So the architecture in that respect is reasonable cross-platform. In the end, what is the difference when it comes to, so the problem in the end which you solve is the same thing, or it's all want to sort of, well, in the end want to play some sort of pulse sheet or maybe a gate sheet, or which depends on the strict timings. So this area of concerns, I think, generalizes to all the different platforms. Of course, there are differences if you then dig deep, but they are not necessarily on the synchronization, sort of not on these main concerns that are really challenging now, or that have to be solved, but they're more like on specific instruction sets which you make available then when you play a certain pulse, for example, or do you do a phase or a phase chirp when you want to move atoms around, or have a very short, very well-timed high-fidelity pulse when you operate a superconducting qubit.
Yeah, cool. Thanks for that. Frank, let's move on to you. What are the main technology challenges that IQM is having to consider as you scale your systems and move on to think about error correction?
Yes, Neil, thank you for this question. So IQM is not only quantum processor manufacturer and developer, but also a quantum computing integrator. And as such, we of course have to look at quite a broad range of challenges. And while they're all important, it is very important that then we always find the best compromise in our way forward, the best compromise between all these challenges. But to name just a few specific ones, I would also subscribe to the control challenges mentioned before. They're, of course, in very technical aspects, in like the analog performance, the crosstalk mitigation, especially for scaled systems. These are very hard challenges. But then as an integrator, we also need to see that solutions come with a cost, and actually finding cost-effective solutions for these massively scaled quantum number of physical qubits as it is expected for fault tolerance will be very, very important. Then, of course, fabrication is a dramatic challenge. It's also related very, very intimately to the fragility of the quantum states. Of course, we can build on the experience of the semiconductor technology, of all these lithography and production scale machinery and methods they have. But then really like working with the superconducting materials and really protecting these very fragile quantum states on a physical level to a sufficient degree to even start error correction, start thinking about error correction, is a very dramatic challenge, and a lot of learnings in scaling here will be necessary. And all already these two challenges show that we should also work on the conceptual level. You've already mentioned the QLDPC codes, and there's of course an important reason why we look at them, although they are more complex and more demanding in connectivity. We want, of course, because they offer more hardware efficient encoding, and these are really the tricks which can at some point bring us to the level of physical qubits, which is still conceivable with a reasonable engineering path to build these utility scale quantum computers, which will have industry relevance.
So we've got a question on QLDPC later on, but diving back to, you said having to trade off various, make compromises there, and you brought up costs. So as we scale, so how much does, so obviously as we have a utility scale system, that we're going to have to think about costs there. What's your sort of perspective of how the ecosystem, so I'm not saying necessarily IQM in particular, but how should the ecosystem think about costs? In bluntly, should we sort of spend as much money as we need to spend to actually make the thing work? And then at the very end, sort of like, let's try and make it cheaper? Or do you think throughout the process as we develop, we should be trying to minimize cost as we go?
It is probably a combination of both. While we need to be fast enough, the challenge is so enormous that it can drive us into cost regimes which are simply not practically sustainable anymore. Even sort of in this highly forefront of technology or very deep important technology development. So when at some point you multiply everything, for example, all the cost per qubit with 1 million qubits, then you easily come into the billions or tens of billions or hundreds of billions if you are not careful, and then this is just not realistically scaled. So it's a boundary conditions we need to consider. We need to bring this also the cost into a conceivable and reasonable regime. And this is part of our compromise. But within this regime, we also have to see that we are fast enough.
Absolutely. Thanks very much for that, Frank. And Ben, so moving to your technology, which is obviously different. So the AMO, neutral atom technology, which obviously has different challenges. What are the main ones that you see from your perspective?
Yeah, thanks, Neil. So a really interesting question. And I think with neutral atoms, we are rapidly scalable and already have very significant qubit arrays today, and these will grow very rapidly because these are really linked back to the laser systems and the way we shape those laser fields and control fields to address atoms. Now that presents one of the challenges, and that's how do we take QEC that we are really starting to do on a small scale now and keep up with that incredible momentum that AMO or neutral atom platforms have. And there's a significant challenge to that, particularly with codes where we going beyond surface code, we don't understand everything about these codes. For example, how to do all the logical operations. So there's a real challenge there for QEC to extract the best error correction performance you can from the potential that neutral atom machines offer now and will do in the future. I think the other big challenge is the level of flexibility they offer in their architecture. This might seem like a luxury, but and allows you to do things like QLDPC codes, which we can talk about more on in a bit. But we want to make sure we retain that agility. We don't know all the solutions with QEC, right? We have surface code implementation where we know how to do QEC, and we have emerging very interesting implementations of codes where there are still open questions. And so we must make sure we design our systems that are agile to be able to perform well around different codes and optimally around those codes. I think another thing you touched on earlier is with that all-to-all connectivity we have with neutral atom platforms and AMO platforms is that we need transport to have that long-range connectivity. And transport itself has a cost. There's a time for every move you do. So you need to work out how to minimize or optimize the amount of transport you have and fold that into your QEC cycle. This is something where, Infleqtion in particular has an in situ architecture, so where we can do entanglement on neighboring sites without transport. We have that ability, we have that option. And then when we need to do transport for logical operations over long-range connectivity, we can do that too. And that's really trying to take an approach where we can optimize the level of transport you need so you can use it where it gives you a really strong advantage.
Thanks for that, Ben. You mentioned something that I thought was really interesting. You kind of talked about like one of the great strengths being a sort of also, not, I don't mean weakness, but a sort of a challenge as well. So the flexibility of the system, and that flexibility almost gives you so many options in which you could go, directions you could go in and how to implement logic, right? And then, so you want to maintain the agility to be able to try out different things, but then how do you balance that with making firm decisions on how you scale? So like at Riverlane, at various stages along our roadmap, we have to make decisions. We are going to do it this way, right? So how do you balance that, maintaining the agility, but also making these decisions to make progress and actually go forwards in your technological development?
I think a really good approach, and is one actually that really is very useful in all science and technological innovations, is having some concrete or a concrete example to coalesce around. And in this case, it's having some idea of applications in mind. And so we've published results on material science applications, for example, and that's somewhere I think the industry as a whole sees as some of the earliest applications where we're going to see real-world utility for fault-tolerant systems. So when we think about these applications and we think about how we can encode them, we think about how we do QEC on these, that's where we can really start to see what are the benefits of using different codes or a combination of codes in different ways. And that can really help guide our decision making. Now, on the hardware level beneath that, we want to maintain that agility so we can support different codes. And so that's where decision making comes in for that. But really then using those sort of applications to focus it in on what are the next steps, particularly when it comes to QEC implementation.
Cool. That's a great perspective, Ben. Thanks very much for that. Okay, so we've mentioned, so QLDPC codes have been brought up a few times. So we know that they promise lower overheads in the surface code. There's an exciting developments that are happening in the literature just now on how to do computation with them. But from the hardware perspective, what are the biggest practical barriers to implementing QRDPC codes? And do you see a realistic path to overcoming them? So let's start with you, Frank, given that I think superconducting qubits potentially have the hardest challenge in implementing QLDPC codes.
Yeah, thank you for this really great question. Indeed, because we have fixed connections and cannot shuttle our qubits around, we need to think very carefully. And so the price to pay for the connectivity is the hardware complexity. And for this reason, we have invested a lot of effort into code engineering and have come up with very specific variants of the QLDPC codes, which build on one of our high connectivity, on the recently shown high connectivity hardware platform, so on our Constellation architecture. And they actually use an improved local connectivity in the plane over the simple square grid when you use additional couplers to break this planar picture, to keep this hardware overhead and the fabrication complexity as low as possible. And this has been recently also shown in one of these, in the paper by MIT, that the hardware complexity of the IQM codes is really low. And the ones which we are tailored, which are not in there yet, and which we have tailored towards to our constellation architecture, have an even lower hardware complexity. It is still challenging, but it is much, much better than what you would naively think from the codes you find in literature.
So it sounds like you've also got some secret codes up your sleeve that you've not quite talked about publicly yet. So it'd be really interesting to hear about them sometime soon, that's for sure.
Yeah, actually, it is not secret. Actually, there was a talk on the March meeting, but the publication is not out yet.
Okay, I wasn't at March meeting, so that's great to know, Frank. I'll have to check that out when it's online. Cool. And Ben, what about you? So we've touched on QLDBC, like you said, like you've got the ability to, with the reconfigurable arrays, that the long-range connectivities are somehow easier. But are there specific challenges in QLDBC codes that your hardware will have to overcome?
Yeah, I think it really comes back to optimizing that degree of motion, and really modeling how that motion affects your overall QEC cycle. As you scale these systems, the overhead for any step of motion is actually the acceleration of atoms and deceleration of atoms that has the cost there. So you have an overhead with every move you make. So it's really thinking about those hardware constraints when you come to optimize the implementation of a QLDPC code. And so that's where, it's really important that we work, broadly to understand these codes, understand logical implementation of these codes, and really look at how we can optimize that on these systems. I think another point of neutral atoms is that we have to proactively manage atom loss as well, and that falls back into then a slightly more complicated way that we can read out, because we're not detecting just the qubit state, but the loss as well, and then how we fold that back into that QEC cycle. And that, I think, also presents an interesting challenge. I think Riverlane as well, you've been doing some work on this and have publications on this also, to see how we can do that with maximal efficiency. So there's great potential here, but really, yeah, it's a space we really want to explore and optimize.
Yeah, and that's really interesting. Like you mentioned about the trade-off. I think I understood this correctly. The trade-off with almost how much shuttling you do, the degrees of motion. So it's kind of like, it almost says maybe potentially that you don't necessarily want to say you've got all-to-all connectivity, but you have very substantial connectivity. But maybe by leveraging all of full all-to-all connectivity, that might come with too much of a cost. Is that a correct way of interpreting what you said?
I think what I would say is we have all-to-all connectivity, but we don't need to use all-to-all connectivity all the time.
Yeah.
So we can entangle neighboring gates with our in situ architecture without any motion at all. And where we need to use long range connectivity, that's where we can utilize that. So we have both options there, but the question is, how do you take advantage of that in the best possible way? How do you optimize when you use the all-to-all connectivity? Because it has great benefit, but it also has a cost associated with it.
Yeah, cool. Thanks very much for that, Ben. And Tobias, from the control perspective, I must admit, I actually haven't seen much in the literature that is discussing control implication for QLDBC codes. So I'd love to hear your perspective on that. That'd be great.
Yeah. So when it comes to sort of enabling QLDBC codes, I think the challenges maybe specifically here are not that grave than when you go to the QPU. So essentially, to be honest, we feel pretty comfortable that we have the right infrastructure here in control hardware, but also in software to support researchers to implement these QLDBC codes. And when you mentioned, for example, this was now mentioned a few times, this non-local connectivity. Here for us, it's reasonably simple. Or we built now in our very big sort of footprints where we have in one shelf more than 360 channels which can directly talk to each other and exchange information in real time. And then only with a few cables, you can actually extend this all-to-all connectivity then to actually multiple shelves in a full mesh, and then potentially have very quickly several thousands of channels talk directly to each other. So that is something which you have to deliberately choose, because making such a large system is, of course, one of the trade-offs which you have to do. But I think here, when it comes to quantum error correction, I think we are very well set up to support this sort of non-local non-local connectivity and be able to shuffle information around very quickly. Maybe a challenge which is much more than on the hardware side is maybe then on the software side. Of course, you need then also compiler, which then take the problem that we get from the researchers and compile this down to the system. And here again, there will be much more. This will be much more of a challenge to understand sort of the shortcuts which you can to the specific optimizations to the concrete architecture, and how to efficiently compile this down. And this essentially is really one of the problems which we're going to face, but not in a general favor, in this very collaborative way, on how do we make sure that this flexibility that we have actually is modified in a way that it actually works very well for the partners here.
Yeah. So in that, are you sort of are you developing that flexibility just now, and do you think that flexibility needs to be maintained as we go forward? Because, like, is that a critical feature of your system, or is that a feature that's really useful today in this sort of more exploration era, where we're trying to see what are the right QEC codes that we should be using, try out one, try out another? So how much flexibility do you think you need to maintain as you scale?
Yes, looks like I think going forward, this is we would have to go down here in flexibility. This is definitely, it was an absolute deliberate choice to really support this current challenge of, okay, we don't know really what the architecture is, and now let's see, put the least barriers sort of to the system or to the researchers, that they can explore exactly different connectivities, different types of decoding, hierarchical or distributed decoding. And then at some point, once the architectures might get more clearer, then maybe we can make more to probably reduce this flexibility. I think if we go ahead and think about the next scaling challenges, very clearly, I mean, these systems will look differently if you look at them. Nonetheless, I would say the backbone, the architectural backbone where you have sort of the separation of concerns will stay, because that's sort of it's a natural symmetry in the problem that we have to solve when we program these quantum systems.
Thanks very much. Well, as expected, I had more questions than I could get through. So the conversation's been really, really interesting. It's been flowing really, really well. So I'm glad that we managed to dive deeper into some of these questions. We're now going to progress onto our second panel. So thanks very much, Tobias and Frank and Ben, and we'll bring you back in for questions at the end. But let's move on to the second panel session, where we're focusing more on aspects considering HPC integration and also artificial intelligence. So we're really lucky to have Krysta Svore from NVIDIA, who's the VP of Applied Science there, and Masoud Mohseni, who's the Director of HPE Quantum. So again, as we did before, Krysta, could you perhaps introduce yourself and say a couple of comments about what NVIDIA is up to in the space of quantum computing?
Yeah, absolutely. And thank you, Neil and Riverlane for hosting this great discussion today. So I lead our applied research for quantum computing at NVIDIA. And at NVIDIA, we really think about advancing accelerated computing, right? We're thinking about how to enable quantum GPU supercomputing, how to bring in QPUs to a very heterogeneous compute environment. And so we're looking at everything from how do we help use advanced accelerated compute to stabilize qubits and understand the errors, How do we integrate a system, a QPU, into an AI supercomputer? And then how do we then program and enable finding great applications for this? So we think a lot about how to bring AI models into the mix and how to use AI models to advance and accelerate the development of quantum computers and scaling them, but also then how to bring information back from quantum computers into AI models as well.
Cool. That's great, Krysta. And Masoud, on to you now. Some words about yourself and HPE and their work in quantum computing.
Yeah, thanks for invitation and hosting this event. Very nice discussion. Yeah, so I'm leading quantum team at HPE, and what our mission is to bring quantum AI and HPC together in a full stack, tight integration. We are going to be agnostic to QPU and the underlying QPU modalities, as well as quantum SDKs. We are agnostic to both. We plan to meet quantum vendors and customers or users where they are. And we have a top-down approach to kind of building quantum supercomputers. We think that we should focus on the actual applications and in what way quantum computers are going to be useful. And in that way, we can be like go-to-market strategies for various different quantum vendors.
Okay. That's really interesting, Masoud. Thanks for that. I'm definitely interested in this top-down approach. Maybe we dig into that a little bit. But first of all, so you both mentioned like the future supercomputers in some sense, a QPU being a node there, right? So we all believe, I guess, I hope we do, that it's going to be the future supercomputer is going to be a hybrid of quantum and classical computing, but there's going to be many challenges there. So what components need to be tightly integrated and co-designed, and which parts of the stacks can be modular? So let's start with you, Masoud.
Yeah, so when you consider HPC and quantum integration, we need to kind of distinguish between different layers of stacks. At the lower layers, you would say HPC, and we can discuss about the role of AI later in this discussion. But the contribution of the HPC and HPC compute and HPC networking is to enable quantum computers to operate at a scale. That means calibration, control for real-time calibration, real-time control, real-time error correction. You need lower latency communications, like 100 nanoseconds for real-time control, around probably a few microseconds for real-time decoders, at least for superconducting qubits. And there are issues where that HPC has to be, kind of obviously tightly integrated. You can even combine calibration, real-time control, but and also even have a hybrid of calibration and real-time decoders. But once you go to higher level stacks, you need also HPC for quantum error correction orchestration library and workload management, and all the way top to the application layer. We envision a heterogeneous quantum classical computing where the role of classical compute is more than just pre-processing or post-processing, but rather would be a co-processing that they exchange, even bit string or solutions between QPU and HPC and on, orders of magnitude operation iterations that could be even 10 to 8, 10 to 10 iterations to converge to a solution. And for that, the latency even at the application layer becomes important. So the requirements are very tight at the lower stack. Then that there is no dispute on that. For application, there would be certain application that quantum computers for FTQC machines that's going to run over like days or weeks, and for that, remote access would be sufficient.
Yeah. But it's interesting there. So like just to touch on this a little bit more, like you said, you've got a top-down approach at HPE where you're thinking about letting algorithms drive and problems that you're trying to solve drive what the sort of architecture should be in some sense. So you think there's going to be a really important interplay between the QPU and the HPC in actually solving the algorithm, right? So there'll be some classical component being solved in the HPC and some part being solved in the QPU. But importantly, what you're saying, I think there, is that there needs to be a back and forth communication. Did I understand that correctly?
Yeah, so you can think about, for example, sampling discrete spaces, there are certain hardware accelerators classically that, let's say, in the context of probabilistic computing, you can have FPGAs or custom designed ASICs that can sample like hundreds or thousands of, let's say, spin updates per nanosecond. And this is super fast, and quantum computers are not necessarily good at that. But this is usually better for exploitation. And if you want to do exploration, at least when there is absence of a structure, like you have this kind of shallow thin barriers and a lot of them scattered, and or when you have these saddle regions, quantum processors could, explore those kind of unstructured subspace in the solution space much faster. And you can consider that there's a continuous exploration with quantum computer, which passes, and for faster exploitation, if we are talking about problems of hundreds of thousands of variables, it might be much harder for quantum computer to do exploitation, but like a probabilistic computer can do much faster. So you can also accelerate this with GPUs, and you can consider a heterogeneous setting of quantum classical computing where CPU, GPU, FPGA, and QPU work in concert, and it's in the application workflow development. Another example would be, let's say, if you want to do quantum phase estimation, you need to prepare initial state that has very good overlap with the target state, and some of those calculations could be very expensive, and you might need to push the classical compute to the limits, even exascale, to get to certain kind of high overlap with the initial state, to get to initial states that have good overlap with the ground state for, let's say, more large molecular exploring, for material science discovery. And that we have workflows that shows that could need to be interactive, and the algorithms are inherently iterative. So it's not like you have a one pass and you just go home and wait for quantum computers to finish the computation.
Thanks very much for that perspective. And so, Krysta, I think the language you used was the AI supercomputer. I mean, there's many different terms for the supercomputer, but I think that's the language you're using. So, from your perspective, what does that future supercomputer look like with the QPU node in there? And which parts do you think need to be co-designed, and which parts do you think can be sort of modular in some sense?
Yeah. I think, building on what Masoud just shared, totally agree. There's this, I think of it as this tighter, inner loop, this tighter integration loop for the real-time system. And then you have more of the application loop, right? Where you're communicating between maybe the supercompute, a larger supercompute node, the larger supercomputer, right, with the logical QPU. And I say logical QPU because I see that for applications, for truly advantageous applications, we have to have quantum error correction. We have to be stabilizing the qubits. We have to be decoding and understanding the errors that are happening while we're computing. And so when we think about that piece, right, that's this tighter loop that we need, this tighter integration and feedback between the QPU and a real-time host. And here, this is where in the fall, this past fall of 2025, we shared an open reference architecture called MVQ Link on how to go about integrating a real-time host. It could be, a single GPU, a CPU, it could be a combination, it could be a node, right? But this host then needs to integrate with the QPU, right, by way of the controller. And so we released an open reference architecture to enable this to have and really specify such communication and integration and enable that low latency there. And then what does this enable, right? When you look at the real-time needs of the system, this involves things like how are you going to tune and calibrate the qubits and the various knobs, right, the various parameters in your quantum system while you're computing. And at the same time, you have classical information coming from the QPU, right, in the form of, we often say, syndrome bits. But you have classical information, these classical bits coming from the QPU that then you, of course, decode, as you've talked about already, Neil, in your roadmap as well. And so we need that real-time system, and those are the very critical pieces. I think the really exciting direction here, when I say AI, right, AI can be running, both at the application level, right, where we're looking at AI for the algorithm itself, the application we're running a mix of AI, right, or maybe we're taking data from the QPU to train an AI model, but we also can have AI native throughout the stack. And for example, we've just released NVIDIA Ising, which is an open family of AI models, really targeting the needs of this tight integration, right? Really targeting the needs of stabilizing and making reliable qubits. So this includes an open model, really an agent for calibration of the qubit system and the qubits, and then also a decoder based on convolutional neural net that can be used in conjunction with other decoders to speed up the decoder itself and offer improved accuracy. So we can see up to 3 times faster and up to 3 times more accurate capabilities from using this, what we call pre-decoder, which is in this Ising family of open models.
Yeah, that announcement of the Ising model is really interesting, and it was great to see your day, the Quantum World Day, and the various talks around that. On that though, Krysta, in terms of, so it's really, really interesting work that's happening there. I think certainly everyone, so as we've mentioned before with AMO qubits, the QEC cycle time is certainly slower. So, and the AI models and the AI decoders certainly seem that they can keep up with the QEC cycle time of, say, roughly a millisecond. Potentially those QEC cycle times do actually reduce for AMO, but I'll let people in that community comment on that. But for superconducting qubits, or like fast qubit types, where it's 1 microsecond possibly, it seems like kind of we're at the, it seems a challenge so far in the literature, I'd say, that these AI decoders and what have you can keep up with the rate at which the syndrome measurement data is being generated. What's your expectation that either improvements in the sort of decoding architecture for, say, an AI decoder, or are there actual potential improvements in hardware on which these decoders are run on? What's the sort of that landscape that could potentially overcome these last hurdles to get that tight real-time loop for fast qubit types?
Yeah, so for fast qubit types, right, even with the what we call the pre-decoder, this NVIDIA Ising decoder that we've released, really you pair it with what we call a global decoder, and then overall this can speed up the full decoding problem, right? And so while we still want to bring the decoder latency down, you can, with these, the whole idea of this pre-decoder is to, in some sense, lighten the load for the global decoder, right? So that the global decoder can run faster. And in many, I used to do a lot of work in machine learning for information retrieval, for web search, right? We would run kind of these fast filtering techniques, and then a more expensive, processing on, say, the queries and retrieval of web pages. It's very similar here. Like, I think we're just starting to explore the landscape of, hierarchical decoders, more interesting distributed decoding architectures, where you're really able to combine different approaches, combining AI model with a more algorithmic decoder, with maybe a heavily optimized, more hardware specific decoder. And so these can come together. And so what we see is we can improve upon the speed of, say, a very standard global decoder, like, say, a matching decoder. We can really improve the speed, lower the latency, and have high throughput when you combine it with an AI pre-decoder. Now, we're looking at today's technology when we're benchmarking that pre-decoder. And so indeed, recently, for example, in our hardware roadmap at NVIDIA, we've started to introduce these fast inference capabilities with this LPU and the Grok technology. And so indeed, you know, as even classical hardware continues to move and become more performant for inference, that can apply here as well and offer continued improvements. And so, you know, this can be a technology. AI decoders, I believe, will be a part of, you know, every decoding path. The question is, you know, how is it combining? How are we using it with other decoding systems as well? So ultimately, I think of this as a, you know, it's really a system of decoders that can be paired with the technology Riverlane's introducing, for example.
Yeah, I had a nice chat with Chris Chamberlain, who's one of the authors of this pre-decoder work. And he was mentioning to me that the likely where this pre-decoder work that you guys have been working will really shine is when we start thinking about doing logic. So I mentioned on our roadmap, you know, starting off with Clifford logic and then potentially, and then obviously onto non-Clifford logic. And I think that's a really interesting place to explore. It'd be really interesting to see Riverlane and NVIDIA working together on that, seeing how this pre-decoder integrates with QEC systems that are implementing logic. So it's really exciting stuff that's happening, and lots of interesting problems to still try and solve there, definitely. Cool. So you mentioned some of the AI having some big impact in the space of real-time error correction and pre-decoders, Krysta. But what about in other ways that AI can help accelerate quantum computing, and particularly accelerate the development of quantum computers? So could you maybe touch on that, how AI, so not necessarily about pre-decoders, but other aspects where AI could be used to accelerate the development of quantum computing?
Yeah, absolutely. So, you know, I think AI is such an amazing, we're just so lucky, right? We're so lucky to be developing this technology while AI is accelerating in such a big way. We can use AI really throughout the entire stack. I think about using AI not only to stabilize and create reliable qubits, but then using AI to help design that system. And so earlier there was, you know, discussion in this conversation around, you know, co-designing the system with the application. And ultimately, we want to do extreme co-design through the whole stack, right? We want to take into account the application needs. We want to take into account the hardware constraints. And then we essentially want to design, you know, a full architecture that leverages you know, the best of the hardware while, you know, enabling that application to run with the best hardware utilization, you know, with few numbers of qubits, et cetera. And so we can drive this extreme co-design with the help of AI. And we're looking at things, everything from AI for algorithm discovery, right? How do we go about finding new applications? Can you use AI to find and even prove that quantum advantage exists for a new set of applications? You can also use AI. We have some techniques that are called things like adapt GQE, generational quantum eigensolvers. You know, here you're using LLM models to in fact find shorter, you know, lower depth quantum circuits. And so here you can see that AI can be used to reduce the depth of say, the algorithm of the subroutine, the circuit you're going to run. I see this as having forward application even when we think about how to run quantum error correction. How are we going to go about finding better syndrome extraction cycles? How are we going to compress, right, the cycle for logic in quantum error correction? We can find better lattice surgery techniques. We can find better syndrome extraction, right? All with the aid of AI. And then I think about AI, you know, also helping us reason over, you know, over the best architectures, you know, different logic architectures. So right now in the, you know, in the field, it's amazing. Almost every day there's a new microarchitecture, a new logical microarchitecture coming out in, you know, on the archive. And we want to be able to understand those architectures, what pieces of those architectures are relevant for other hardware. You want to pair different ones together. You want to be able to reason over, you know, should I be using hot, cold storage? You know, what distance should I use for memory? Can I take that memory component and combine it with this logic component? And I think AI can really help us reason there as well.
Yeah, it's definitely, you touched on all these really great results that are coming out in the literature at the moment on how to perform logic. And one of the things that I find quite fascinating about that is that's just human ingenuity there. And then I don't think AI has been thrown at that yet. So it's just, if you throw AI at that, how many papers are going to be coming out in the archive? I have no idea. So that's a bit of a scary thought in some sense for people who are trying to keep up with the literature, that's for sure. Okay, so Masoud, let's sort of transition to talk about how the quantum ecosystem could potentially be more collaborative. So you set up this quantum scaling alliance, which Riverlane's a part of, which we're really proud to be a part of, and it's super interesting and exciting. So what other mechanisms need to be set up within the ecosystem to enhance collaboration, and are there any downsides to companies working closer together in some ways?
Okay, so yeah, the idea that we had, like, that was 3 years ago, we started having conversation that this kind of current approach of a vertical integration of quantum across all the stacks is just not going to scale to kind of building quantum computers that could contain millions of qubits. The problem is that once you have this vertical integration, you're kind of you're exposing yourself to a lot of risk that is kind of harder to overcome as you scale the system. In contrast, horizontal integration, which I can define, and this was the basis for the Quantum Scaling Alliance that I co-founded with John Martinez at Colab and other companies, including Applied Materials, Synopsys, 1QBit, Quantum Machines, and Riverlane, and some academic kind of institutions like University of Wisconsin and UCSB. So the idea was that we can join forces to build a scale at the system that, in a way, we bring the best in class from various different quantum vendors, and we do not necessarily have to bet on any particular QPU modality, quantum control, or any particular quantum SDK. We can have the entire ecosystem to work together, establishing standards and sharing data that are not proprietary, and being able to design open quantum software, open architectures, and accelerating R&D. So they are like this is reducing the R&D costs, obviously, but it would reduce even manufacturing costs. Or when you, let's say, bringing the HPC integrators, there are like decades of experience and like know-how to bringing this kind of system to the prime time. You don't necessarily have to double down on the mistakes. Usually when there is a vertical integration, it would be harder to pivot from, let's say, one modality, QPU modality, to another one, if there are evidence that this different modality performs better. But horizontal integration has actually been around in conventional semiconductor technology for decades. And it's not clear why we shouldn't adapt that in quantum computing. Of course, there are certain risks, IP leaks and other issues that should be addressed. And in general, at the end, these companies have to make money, and they have to make sure that there is some value proposition that they maintain. But we find that it's possible to coordinate and kind of get convergence for our incentives across community. So I think this is the way to go, especially if we facing various different challenges that are mostly overlooked or underappreciated. When you go from like tens of thousands of qubits to 100K and then millions of qubits, this is kind of the HP's focus to scale at the, considering challenges at the order of millions. And I want to mention some of this actually, coming back to kind of the role of AI that was mentioned, Krysta addressed a lot of possibilities for role of AI in quantum. Basically, I fully agree that AI can play roles in every single layer of stack. And that's actually one of the things that with the horizontal integration, you can bring various different state-of-art generative models, like based on transformers or diffusion models, into the kind of pipeline. And I can tell you there are opportunities that even, Krysta mentioned a lot of them, but there are some more I can add. For example, you can use AI, beyond the algorithm discovery for workload management. And basically, we are building an entanglement hypervisor that is looking at entanglement heat map in the runtime and allocates, various different sub-problems to quantum classical processors based on the amount of entanglement they contain, because standalone quantum computers would never be that big enough and cost effective to tackle problems at the scales of millions. It's unnecessary if they're just like a low entanglement regimes. You want to compute that on a classical machine. When you come down in the even approaching quantum recursion orchestration library, you want to manage things in real time. An AI model can absorb, use information, let's say from an emulator on the runtime, and do like concurrent compiling and execution. So the systems becomes more adaptive, and I think you need to get to that kind of technology to build larger scale machines. Since as you scale quantum computers, that it's not the like best case performance of qubits matters, or medium performance. It's like the worst case, the tail of 1% of worst qubits could actually cause problem. And you need to identify this all the way from calibration to real-time decoding to connect with, a workload manager that is aware of the hardware constraint, and is also aware of the algorithmic requirements. And this is related to this kind of holistic co-design. So I think in addition to bottom-up approach, we think you need to have top-down approach. And, you obviously have to iterate between this. And we believe that like a horizontal integration where you bring the best in class from each sector of the industry, you don't need to reinvent wheels, and you don't need to basically repeat things that is possibly been done in another startup or another company, and brainstorm and set up standards and define APIs at various different layers of stack to build the entire system and accelerate the R&D process.
Thanks very much, Masoud, and thanks very much, Krysta, for that part of the panel. As expected, we're a little bit over time, but I think we're going to have time to try and get a few questions. If people are happy to stick around for a little bit, please stay online. So let's bring in all the panelists again and thank them all again for all the great contributions. So let's see how I go with tech again, right? So there's, let me see. There's a question by Anonymous. This person keeps asking lots of questions. The latency requirements of fast versus slow architectures are typically assumed to be vastly different, 1 microsecond versus 1 millisecond. How realistic is that one decoder control architecture can be right for both? Okay, so let's go to Tobias, given that we're talking about control systems there. Do you believe that one control architecture is going to be able to solve all solutions for all qubit modalities?
Yeah, no, I don't think that this is actually realistic. And maybe there's certain concepts which you can transfer. In the end, we talked a lot about co-design here. In the end, parts of the algorithms to the higher levels of the stack or have to be really co-designed with a specific architecture and specific sort of shortcuts which you can take maybe in your specific choice that you do, which will then allow you to reap benefits sort of exponentially, for example, when you then operate below threshold. So I don't think that there will be one architecture, one decoder. I think it will always be different flavors which are really designed then together with the specific choices that you do. And this will probably be actually one of the significant differentiator between maybe different computers in the future which will compete against each other.
Riverlane has a similar mindset. We definitely think, like, say, between like QLWC running on AMO and say like surface code running on superconducting, those two QEC architectures are probably quite different. But we believe that it's going to be, we know that we can learn from one architecture because we work across the whole stack. We can we have learnings for one particular architecture that we can then implement in another. So we've done that in the past, and even though we don't believe there'll be a uniform architecture, we do believe there's a lot of learnings that we can get from each of them. Okay, there's a nice question to do with neutral atoms. So this is directed at you, Ben. What are the fabrication-related challenges for neutral atom-based hardware, and how can they affect the performance of an error-corrected device?
Yeah, thanks. That's a great question. I think there's two parts to it. There's the near term, which I would say is in the next 2 to 4 years, and then there's the long term challenges. And in the near term, really, it's about widening your field of view for optical addressing. And so you can scale up your compute arrays relatively simply with more power, but you also need to make sure that you can do this very precisely with a low degree of optical defects or aberrations in that. So there's a lot of work that we can do with optical design and suppliers on that. And then in the long term, there's a really interesting opportunity here, and this is really starting to pick up on photonic integration. And this is where we'll go beyond thinking about scaling of 10 to the 4, 10 to the 5 physical qubits to far beyond that. And then there's a longer term challenge there, but it's a really exciting time in the photonic community. For a long time, there's been photonic and atomic integration, but really productionizing that and building that into our control, into our technology stack would be a very good thing to focus on in long term.
Cool. Thanks for that, Ben. I have another question from Anonymous. This says 4 votes. I think this will be directed at you, Frank. So when you're linking delta flow with IQM or Infleqtion, but let's think about linking with IQM, how difficult is that? And what challenges do you have? So I have a perspective, but it'd be interesting to hear what your perspective is, Frank.
Yeah. I mean, a lot of the difficulties are probably in linking it to the control electronics. And when linking it to the IQM systems, the main work will, of course, be in integrating it in our software stack, which kind of goes hand in hand. But I would not identify any delta flow specific integration problem here. It's generally important that decoding opportunities are integrated well into the software stack in a modular way. Yeah. But the hardware integration is probably a lot with the control system.
Yeah. So, like, from our perspective, we've developed the QEC interface. So what that essentially is a interface that allows the error correction system to be modular. And so the actual interface itself to implement is a good hardware engineer actually can do it in half a day. So that's a lovely statement that all my hardware engineers always tell us to say. But there's some complexities to this. So we have the sort of physical layer, the protocol layer, and the data layer as well. But interestingly, Krysta, you mentioned NVQ-Link as well. So I'm not saying, I don't think these interfaces are necessarily competing with each other. I think there should be industry standards. That's the sort of direction that I think the ecosystem should go in. So obviously, NVQ-Link is more than just an interface, but an important part of that is the interface. It'd be interesting to get your perspective, what you think about industry standards for interfaces and what have you.
Yeah, I think it's very important that we work together on moving towards agreed upon interfaces, whether those reach, at this time, kind of that standards label. Yeah. But I think we need to move in that direction, and in particular, because we really do want to have, components that can operate with other components, right? We want to be able to bring in, for example, with MVQ Link, we want to be able to work with any control system, any qubit modality, right? We want it to pair with Riverlane's decoding capabilities and technologies. And so it's very important that we agree upon interfaces. I think looking ahead, right, it's even more important to agree upon interfaces and representations because of the explosion of AI and agents, right? We can enable more agent-driven capabilities if we have well-defined interfaces in the industry. And I think that's a huge opportunity for us to come together around. Masoud mentioned, moving towards some more open sharing of data sets and benchmarks. I think, part of our intention in sharing open models, right, with NVIDIA Ising, and behind that, actually, there's an open benchmark QC eval for starting to benchmark calibration, and in particular agents for plot understanding. The more we can share and share open software, open representations, open data sets, right, I think we can really accelerate our innovation. And we see this, in the more general set of industries, right? There's an explosion of open artificial intelligence models. The consumption of those is growing incredibly rapidly, and we have an opportunity to really learn from what's happening in other industries and communities, so that we can advance more quickly together towards scaled quantum computing.
Cool, that's great, Krysta. Okay, so one final question, quick short answer from every single panelist, please. Do any of the panelists have a favorite QEC code? And Frank, you're not allowed to reference the IQM QEC code. You have to reference a different one. So let's start with Frank.
Okay. So that's a different, I mean, all the QEC codes are of course good, but I'm asked for favorites. So currently I find the QLDPC code family as such super exciting.
Okay. Tobias?
No favorite one. The one which will make the first long-lived logical qubit.
Ben?
Been a very, very exciting recent paper on Shor's algorithm, neutral atoms with QLDPC code. I think there's a huge amount of excitement around this right now.
Cool. Krysta?
I'm really excited about bringing together different codes so that you have codes for memory, codes for logic, codes for non-Cliffords, right? And really understanding how we can get an even lower set of resources by consuming different codes for different things.
Cool. And Masoud?
Yeah, so there's a lot of excitement for QLDPC code, but I've learned that the excitements are usually a matter of trends and based on the most recent result, and so I don't have a favorite one, and we are monitoring, and I think that there's a lot more to be discovered, and yet we might not have the best, most efficient quantum regression code as of today. So we should be open-minded about the opportunities and possibilities. Yeah.
Cool. Very, very good answers there. Very politically correct as well, in the sense that no one gave a definitive answer. So I really appreciate that. So thanks very much. So a huge thank you to our panelists. We've had some really insightful conversations today around the key challenges and approaches to our shared goal of getting to utility-scale quantum computing. Thanks also to everyone who joined today online for your questions. So there's some links here. So basically, these are the links for all the information that you've seen from Riverlane presented today. We've got a link to the roadmap. We've got a link for information about DeltaFlow, our real-time QEC system, and we've got a link there about DeltaKit, the software stack that sits on top of our real-time QEC system. So thanks very much again to all the audience and all the panels, and goodbye.